This is a very brief lecture from Chapter 14, Kinetics, and it's kind of a diversion. It's about half-lives, which you've probably heard about. And the reason we're kind of making this diversion is it turns out that all radioactive decay processes are first order. And so, since radioactivity is an important application of our everyday life, it's just a few slides to give you some example of radioactive decay reactions and the kinetics involved with them. So as you remember, hopefully from earlier lectures, if we have a first order reaction and we plot the log of the concentration of reactant on the y-axis and time on the x-axis, we get a negatively sloped direct relationship where the slope is equal to negative of the rate constant. And so, as I said, all radioactive decay processes are first order because you are starting with just one reactant, one particle that's splitting apart. And so, nuclear chemists, nuclear scientists, tend to take the first order rate law, which you're familiar with seeing like this, and just kind of rearrange it and call some of the symbols different things that makes it more convenient with radioactive decay processes. So instead of concentration of the reactant, which we designate with an A, they tend to talk about number of radioactive particles. So you'll see N in a radioactive decay be it could be the radioactive count, on a Geiger counter, how many pings you get per unit time. So anyway, you'll tend to see the N, and that just means number of particles. Now just briefly, let me remind you of the math of logarithms. If you look at this first order rate expression, it's obvious we could rearrange it. One way that we could rearrange it would be as follows. Right? Just moving the natural log of the initial count over to the left-hand side. And with logarithms, if you subtract one logarithm from another, you can rearrange it as this. They are equivalent in logarithms. And so that is the favored form of the first order rate law when you're doing calculations for radioactive decays. So back to half-life. Half-life is a time, okay, so it always has units of seconds, minutes, hours, something like that. And it is the time it takes for half of a substance to react, decay, disappear. And so, for example, if you start with a 1 molar solution of something, any chemical reaction or radioactive substance that's first order, and you want to know what the half-life is, you could look at a graph of concentration versus time and go down to half that amount. So if we start with 1.0, let's drop down to 0.5, go over to the x-axis and see how long it took to get to half of that amount, original amount, and there are no units here, 1 minute, 1 hour, whatever the units are. And you can keep doing that. So if we want to know how much would be left after the second half-life, we would do the same thing. 0.50 is now our starting point, so we would drop to 0.25, go over to the x-axis and drop down. And so there you go. And so graph interpretation is a key part of this. It's also convenient to commit this little chart here to memory. That's very helpful if you're stressed for time on a test. But if one half-life is passed, of course, the fraction of original substance left is 50%, or 1/2. If 2 half-lives have passed, the fraction left is 1/4, or 25%. I'll do one more. After the third third half-life. 1/8 is left, or 12.5. So basically, and this'll come in handy when you're doing some of the math problems involved with radioactive decay. To just realize this sequence, you just keep dividing it by half. So if you start with 100%, after one half-life it's 50, then divide 50 in half, 25, divide 20 in half, 12.5, etc. You could calculate half-life simply by using the first order rate law and plugging in your initial value, your initial quantity of material, and you know what the quantity at time t is if you're calculating half-life, right? The quantity at time t is 1/2 whatever it was originally. Okay, so if you take this substitution for the quantity of the substance left at half-life and plug it back into the first order rate law, you now get something that looks like this. And now you can combine like terms. Okay, you have the initial concentration on both sides. So you're going to start out by having something that looks like this. On the left side, and then equals minus KT. Remember the property of logs, that if you're subtracting logs, you can put them in a ratio or fractional form like this. Now that you have them in that form, you can cross out the A sub naught, the initial concentration of the material, and you end up with natural log of 1/2 equals minus KT. This little 1/2 subscripts, it's not anything that involves the calculation. It's just to remind you that's the half-life, okay? Time it takes for half the substance to decay. So the half-life expression for a first-order reactant, which is the formula you would use for all half-life calculations, is here. That would be very beneficial to commit to memory. This 0.693 is simply the natural log of 1/2. Alrighty, I just realized at this point the negative sign should be gone, okay, because the natural log of 1/2 is negative 0.693, and we already have a negative over here, so the negatives cancel each other. So here's a sample calculating half-life for a first order reaction. Very, very simple. Let me go ahead and get rid of this negative sign. If you remember from the last slide, I should have eliminated that in the last step of that derivation. So basically, half-life is simply inversely proportional to the rate constant for a first order process. So if you're ever given the rate constant, it's just 0.693 divided by it. Okay, so in this case, and pay attention to the units for the rate constant. In this case, there's seconds in there, so the answer you're going to get is in seconds. So if the problem's asking for units other than seconds, you're going to need to convert it. Here's one for you to try. Okay, you're given the half-life, and you are asked to calculate rate constant. And I should have mentioned in this that it's a radioactive decay so that you would have known its first order. So go ahead and put the video on pause and see what you get for that. Pay attention to units. All right, so clearly, if the formula for half-life is 0.693 divided by rate constant, that can be rearranged so that rate constant is equal to 0.693 over half-life. Again, the only trick here is pay attention to units. Okay, so the original rate constant you're going to calculate is going to have related units to the time that you put in. And so if the problem is asking for different units, you would need to convert. All right, just real quick, here's an actual application of radioactive decay in our everyday life. I'm not sure if you've heard about carbon-14 dating, but carbon-14 is a radioactive isotope of carbon. It's produced in the upper atmosphere where there's a lot of high-energy solar radiation, and it gets incorporated into our atmosphere, carbon dioxide and anything else that contains carbon, and any living substance, including us, animals, plants, will incorporate a certain amount of carbon-14, a known amount of carbon-14, because it's based on the percentage of carbon-14 in our atmosphere, which remains constant. Now, as soon as that live substance dies, it stops taking in new carbon-14, and the existing carbon-14 in the substance begins to decay because it's radioactive. And so scientists can take any substance that used to be alive, and they quite often do this, I've heard it mostly with plant materials, and they will calculate the amount of carbon-14 left in it and then work backwards and figure out when it died, how old it was. So here's an example of carbon-14 dating. A sample of wood has 58% of the carbon-14 originally present. What's the age of the wood sample? All right, so I gave this example because radioactive decay problems quite often will give you a percent left rather than give you an actual quantity that's left or used up. And that's very easy to work with if you remember the nuclear version of the first order rate law. And it looked something like this. So it was a natural log of the ratio of how much substance was left in proportion to how much it started with. So this, N over NO, is the fraction of substance left. Okay? So if you have 58% of a substance left, that means there's 0.58 left, right? Because 58% means 58 over 100, which is 0.58. Okay, so you would just plug in 0.58 for that ratio. You can also work the problem out using the long form of the first order integrated rate law, and I just want you to be aware of that. We didn't really change it. We just kind of rearranged it. But an easier way to do it, if you can remember, is to use the nuclear scientist version. Okay, you just save yourself grief. I just happened to notice that I changed the 0.58 to 0.54 for some mysterious reason over here, so I didn't want that to confuse anybody. And I carry the mistake over to here. Okay, but you're going to end up, I'm not sure which one I ultimately plugged in when I calculated 0.54 or 0.58, but you're going to end up with an age of about 4,500 years. And so that's a common radioactive problem. And so now we will resume our regular programming, which is back to kinetics, but it's just a little temporary diversion into radioactivity.